Welcome to The Explainer. Okay, today we're tackling something every hardware designer deals with, bridging that massive gap between a pristine CAD file and actual physical manufacturing. We're going to break down the exact rules, the math, and the core engineering principles you need to design plastic parts. Parts that don't just, look awesome on your screen, but actually work perfectly out there in the real world. Let's get right into it. So, I want to start off by throwing a pretty high-stakes question your way. Why do so many plastic parts just completely fail on the first try? Seriously, it's so frustrating, right? You wait weeks for the tooling, the first articles finally show up, and they're warped or cracked, or they just absolutely refuse to snap together. Well, here's a surprising truth straight from the factory floor. Most of these manufacturing failures, they aren't material issues, and they aren't process failures either. They're design failures, plain and simple. It's the direct result of creating geometry without really applying the physical rules of how plastic actually flows, cools, and ejects. I absolutely love this quote because it really just hits the nail on the head. The mold is just revealing what was already wrong with the drawing. Design for manufacturing, DFM, isn't just some theoretical check-the-box engineering exercise. It is literally absolute financial protection. By applying the structured rules we're going to cover today, you are saving yourself from incredibly costly tool remakes and totally blown schedules. All right, let's jump straight into Section 1, Molding's Most Critical Rules. As we start building out our conceptual enclosure, the single most absolutely crucial rule you've got to remember is keeping your wall thickness uniform. So generally, you want a nice uniform wall, ideally 1.5 to 4.0 millimeters thick. You really want to avoid walls with wildly varying thicknesses. And here's exactly why this matters. Thick sections of plastic, they cool a lot more slowly than thin sections. So as that thick puddle of molten plastic cools down, it contracts. If the thinner walls around it have already frozen solid, that contracting thick section actually pulls the exterior surface inward. That's what gives you those ugly craters we call sink marks. Or even worse, it warps the entire part because of internal stress. So the golden rule here, you never ever want adjacent walls to differ in thickness by more than 25%. Okay, moving right along to the next rule for our foundation, draft angles. Draft is really just a slight taper applied to the vertical faces of your part, the faces parallel to the way the mold opens. Without draft, your part is going to literally grip that steel mold as it cools and shrinks. When the ejector pins finally hit it, a part with zero draft is going to suffer from surface tearing, heavy scuffing, or honestly, it might just snap right in half. A 1-degree draft per side is pretty much the industry standard for smooth surfaces. Remember, this is a strict functional requirement, definitely not just a cosmetic suggestion. Which brings us to Section 2, adding structural integrity. Now that we've got a solid, uniform, well-drafted foundation, how exactly do we make the part strong? Well, we use internal reinforcements, like ribs. Okay, let's dive into this incredibly important number, 60%. Ribs are just fantastic. I mean, a single rib can easily double the stiffness of your part, and you don't even need a massive increase in the overall wall thickness. But if you make that rib too thick, you create a slow-cooling thermal mass, and boom, you get a sink mark, completely ruining that beautiful exterior cosmetic surface you worked so hard on. So the absolute golden rule of thumb here is that your rib thickness must be 50 to 60% of the adjacent wall thickness. No exceptions. And that exact same logic applies to bosses. Those cylindrical posts we use to accept screws or brass inserts? Bosses are notorious for failing. They strip out, they crack, or they cause sink marks. So to prevent them from cracking under the outward pressure of a screw, which engineers call hoop stress, the outer diameter of the boss needs to be exactly twice the size of the insert's outer diameter. 2 times. And crucially, to keep preventing those sink marks, the actual wall thickness of the boss still needs to perfectly obey our 60% rule relative to the main wall. All right, let's move into Section 3, mastering the snap fit. Now that we're talking about the assembly phase, I've got to say, the snap fit is arguably the most elegant way to join parts together. It totally eliminates extra fasteners, which saves you both time and money on the assembly line. There are a few different types of snap fits, but today we're isolating the most common one, the cantilever snap fit. Mechanically speaking, it's just modeled as a simple fixed free beam. Basically, you've got this protruding hook on the male component that temporarily deflects out of the way during assembly, and then snap, it catches right into a depressed undercut on the female component to lock the whole thing together. Now, when you're designing this beam, what you're really doing is managing maximum strain. But here's the trick. The fixed end of our plastic cantilever beam, It isn't perfectly rigid like a steel beam bolted straight to a concrete wall. Instead, think of it kind of like a diving board attached to a flexible wooden wall. That plastic wall it's attached to is actually going to flex slightly. And because of this flexing, we use what's called a deflection magnification factor, or Q. This helps us accurately calculate the maximum strain at the root of the joint during that very brief moment of assembly.
But hey, knowing your strain is completely useless unless you actually know what your chosen material can handle. Let's say your CAD calculates a 6% strain on your snap fit. If you print that in PLA, which has an acceptable strain limit of 4 to 8%, you're probably going to be totally fine. But if you mold that exact same geometry in a really stiff ABS formulation that taps out at around 4%, yeah, no way. That clip is going to snap right off in your hands. You absolutely must tailor the length and thickness of your cantilever to the exact strain percentage limits of whatever material you're using.
So what do you do if your calculated strain is just too high for your material? Don't panic. You definitely don't have to scrap the design. You can just optimize the cross-section of your cantilever to bring that stress down. First off, simply try lengthening the hook. A longer beam deflects a lot more easily. Second, you can try lowering the beam's overall height. Third, taper the hook so it gets thinner toward the tip. That naturally distributes the bending stress more evenly. And finally, right at the root of the cantilever, always use smooth curves instead of sharp fillets. This is a game changer for preventing stress from concentrating in just one tiny spot. Okay, moving on to Section 4, preventing snap fit failures. Because let's face it, even with absolutely perfect math, real-world applications can be pretty brutal. We've got a few main enemies to watch out for with snap fits. First up is creep, which is also known as stress relaxation. Thermoplastics are incredibly dynamic. If they're held under constant tension for a long time, they literally just relax into that deformed shape and completely lose their holding force. So you always have to ensure your snap fit returns to a totally neutral, unstressed state once it's snapped in. Second, we have stress concentrators. Like we mentioned, sharp internal corners act as a shear point the second any force is applied. And finally, fatigue. Just repeatedly assembling and disassembling a joint will eventually cause it to fail, and often at stress levels way below the material's normal limits. So the crucial point here is managing your weld lines. A weld line forms inside the mold wherever two flows of molten plastic meet and knit back together. Say, for instance, after flowing around a hole in the part. This knit line is inherently weak. The tensile strength right at that line drops to like 75 to 85% of the solid bulk material. If you place a snap fit hinge directly on a weld line, the cyclic strain is going to cause a massive fatigue failure way before the solid material would ever actually break. Always double-check your gate locations so you keep those flow lines far away from your dynamic snaps. And of course, we've got to talk about tolerances. If the gap between your male and female parts is wrong, they just simply won't assemble. So here are your quick, hard rules of thumb. Build in a 0.2 millimeter gap for a really tight fit, a 0.3 millimeter gap for your standard close-fit snap joints, and go with a 0.4 millimeter gap if you're designing a slide fit or a pivot joint. Sticking to these numbers ensures the parts actually clear each other and snap together perfectly every single time. Let's wrap things up with Section 5, choosing the right process. Okay, so we've designed this geometrically perfect part, right? But the physical manufacturing process itself is going to drastically alter its real-world properties. When you compare 3D printing technologies for functional prototypes, the differences are massive. FDM printing is, well, it's fair, but it creates parts that are very weak in the Z-axis. If your snap fit bends against those layer lines, its elongation at break drops by like 50%. SLA printing is pretty good, mainly because it gives you incredibly tight tolerances and isotropic strength, meaning it's equally strong in all directions. But SLS, or selective laser sintering, that's excellent. It uses incredibly strong engineering thermoplastics like nylon, and get this, its slightly grainy surface finish actually provides a little bit of friction, which helps grip those snap fits together even better. And hey, if you're taking the leap and scaling up from a 3D printed prototype to full-blown injection molding, you absolutely cannot forget about material shrinkage. All thermoplastics shrink as they cool down from a molten state to room temperature. Now, ABS is quite stable. It shrinks about 0.5%. But something like polypropylene, that can shrink up to 2.5%, which is huge. That means the physical steel mold must actually be cut slightly oversized by the toolmaker to compensate. If not, your finished parts will be undersized and literally nothing will fit together. And just like that, we're at the end of our deep dive. But before we wrap up this explainer, I really want to leave you with this final, critical question to chew on. Is your next prototype truly designed for manufacturing, or is it just designed to look good on your screen?
By taking the time to implement uniform walls, respecting draft angles, calculating strain, and deeply understanding your manufacturing process, you elevate your work from just drawing to true, impactful engineering. Thanks so much for learning with me today, and I seriously can't wait to see what perfectly optimized parts you design next.